In this video, we are going to do some slope fields, which is the last little section of the differential equations notes packet. And these slope fields are like a little bit annoying and they're kind of a pain, but they're not really hard to do. So yeah, here we go. Slope field, aka a field of slopes, aka that's the graph of the general solution. Like whenever we have a differential equation, right, we can see what the derivative is. We know we could separate and integrate and use, if we had a condition, we could use it to solve for C and get the particular solution. But what if we don't have that condition? What if all I can do is get the general solution? How could we visually represent that kind of in graphical form? Well, that's what our slope fields are going to do for us. So here we go. We're going to go for it. We're going to do this first one. And slope fields are kind of annoying, but they're not hard. It gives us this little grid. See on this first example, it gives us a little grid. And then what we want to do is figure out what's the slope of that function y at each one of those points. And then we're just going to draw a little representative line segment at that point with that slope. And kind of the best way to do this may be to, oops, I don't want to move that. I want to actually write with my pen. Is we probably want a table. So here I've got x, y, and then y prime. So for each one of these points in this slope field, in this grid, we want to figure out what the slope of that graph is going to be. So let's just pick a point. Like how about the origin? If I plugged in the origin, which would be the point 0, 0, I plugged in the x value as 0, right? The x value is 0, plug it in. I don't really need the y value, right? Because that differential equation right here, it's only defined by x. So that y coordinate being 0 doesn't matter. Okay, so let's take the coordinates for this point at the origin, and then let's figure out what the slope of that graph at that point is going to be. If I plug in 0 for x, 0 minus 1 is going to be negative 1. So if I take my coordinates, plug them into that differential equation, which is the formula you use to figure out the slope of the graph at any point, I figure out that the slope of that graph is going to be negative 1. Now what I'm going to do is now draw a little line segment on that point with the slope of about negative 1. Right? Now your slope fields don't have to be super perfect, but a slope of negative 1 in general, should kind of go like that, right? Kind of that perfectly 45-degree, negative 45-degree angle line. Let's do the point right above it, which would be the point 0, 1. Right? So let's test this point right up here. Now remember, the x value is the only thing that matters. There is no y, or there are no y's in my differential equation. So really, this y coordinate doesn't make any difference. If I were to plug in that point right above the origin, 0, 1, the x value is still 0. 0 minus 1 is still negative 1. So then the slope at that point is still going to be negative 1. Right? Those 2 points both have the same slope. The fact that their y values are different doesn't matter because your differential equation doesn't have any y's in it. Your differential equation is only based on x. So the other points in that same column, this one, and this one, and this one, they would all have that same slope of negative 1. That's a terrible negative 1, Steve. Come on. So since that differential equation was only dependent on x, that means the y values don't matter. Right? That means everything in the same column will have the same slope. Because whether the y coordinate's 3 or 2, or whether it's down at negative 1 or negative 50, right? The y coordinate doesn't matter because there are no y's in my formula. Right? Only dependent on x means we're going to have this very nice kind of vertical pattern where everything in that same column will have the same slope. Let's go test. How about the row to the right? Like how about let's test the point 1, 0. Again, the y value doesn't matter, but if we were to test this point, plug in the x value as 1, 1 minus 1, ooh. So that slope's going to be 0. So 0 slopes, those are horizontal lines, so I'm going to make it kind of a little bit extra bold. But then that one's going to be 0, that one's going to be 0. Everything in that column is going to have a slope of 0. Right. Sometimes I like to just take that differential equation, right? Dy dx, that's the same thing as y prime. So y prime equals x minus 1. If I just set it equal to 0, I can figure out where all the horizontal slopes are going to be, right? Anywhere where the graph has this x value of 1, the slope's going to end up being 0. You can find that by just setting the derivative equal to 0. And then if I wanted to test the next column over, Again, the y value doesn't matter. I'm going to stop writing them here. But if you were to test anything in that next column, the x value is 2. 2 minus 1 is 1. So anything in that next column is going to have a slope of positive 1. And what I like to do is usually try to make one of them that's like fairly accurate, right? Try to count one of them so it goes up 1 over 1. Try to count one of them so it's fairly accurate. And then remember, parallel lines have the same slope. So as long as you get one of them in that column with a pretty decent slope of 1, then you can just do everything else parallel to it, and that kind of helps you speed up the process a little bit. All right, so here we had slopes of -1, 0, 1. If I tested the next one, here my x value is going to be 3, so there my slope is going to be 2. So everything in this column is going to have a slope of 2. So from this point, you'd be aiming down here, right? You'd be trying to connect those two. It's going to be probably kind of hard to do this on the smart board, but more or less, a slope of 2. And then as long as you get one of them fairly accurate, you just kind of wing it and everything else is parallel to it, right? Get one of them that's fairly accurate and then just do all the other lines parallel to it. Now, we can kind of see this pattern. We had 3. Sorry, we didn't have 3. We had 2, 1, 0, -1. Everything in this column is going to be -2. Everything in that one, I can't count apparently, is -3. And then everything in this leftmost column is going to be a slope of -4. And so generally, the bigger the slope field is, the easier the pattern is going to be. Here, since that differential equation was only based on x, the y values didn't matter. And so here, everything in the same column had the same slope, and then I just had to kind of test them to figure out what they're going to be. It's the x value minus 1. So here we go. Let's fill in the rest of them. We're going to have slopes of -2. So I'm going to be kind of targeting those 2 points. And that's not terrible. And then do everything else parallel to it. This is a lot harder on the smart board than I thought it was going to be. Oh well. And then the next one would be a slope of -3. So you'd be like trying to connect those 2 points. So it should be steeper, right? The -3 is going to be steeper than the -2. And then the -4, I'm not even going to bother, right? The -4 is going to be pretty steep. So, the slope fields don't have to be super precise, super accurate, right? Generally, if you have like the easy slopes like 1, 0, -1, like those you should probably make pretty consistent, pretty okay. But everything else is like, just count off 1, and then if you have stuff that's parallel to it, you can kind of get the job done. Okay, so everything in that same column had the same slope because it was only dependent on the x. That means the y value, the height of the point, didn't matter. Now, if we wanted to graph some particular solutions, we could. Let's look at, how about this one? Let's do a particular solution. Let's do through the point. Let's do the particular solution through the point. How about 1, -1? And let's go with the particular solution through the point 1, -1. Let's find that point. 1, -1 would be right here. Right? Now, that point is special because that's where you have the horizontal tangent. That's where the slope is 0. So I know there would be kind of something like this. And then there's no real magic to it. You just kind of flow the rest of the graph through the slope field. So here the slopes are going to go up, and they're going to keep getting bigger. And, it's going to look, I don't know, something more or less like that. Doesn't have to be super precise. And then the slopes on the left also going to do something kind of sort of about the same thing. This is a lot harder on the smartboard than I thought it was going to be. Instant regrets. Oh well, still better than doing it with the dot cam. So there we have that particular solution through the point 1, -1. Let's do another one, just because I haven't had enough torture yet with this. I instantly regret doing this. I knew this was probably going to be one of the harder ones, but oh well. Let's go through the point 0, 1. Okay, so 0, 1 would be right here. We can see that this graph looks like it's going to be parabola-ish, which makes sense because the derivative's linear. So yeah, let's go for it. Now we know this parabola is going to have its vertex, the minimum, at the point where x equals 1. So let's kind of graph this parabola. We know that at that point the slope was like 1. Then it's going to come over here. It's going to have the horizontal tangent at some point where the x is 0, right? At some point on that vertical axis, you'll have your horizontal tangent, and then it's going to come up kind of like that. And then that one, I don't know, more or less like that. a different parabola than the red one that we got, but we could graph the particular solutions without actually ever knowing what those equations are. Could I come to this differential equation and integrate it? Yeah, you could separate those. You could divide the x minus 1 over. Ooh, I guess you wouldn't actually, sorry, you definitely wouldn't want to divide that over. You'd want to leave the x's on the side with the x. So you would just have dy equals, okay, it's just going to bother me. It's too ugly. Can't do it. Let's fix it. So kick the dx over, and I'll have dy is equal to x minus 1 dx, and then I could integrate. So 1y is going to be equal to 1/2 x squared minus x plus c, and then there's your general solution. Now, if you had these two conditions, could I use this condition, plug it in, right? Plug in the x value for x, plug in the y value for y. Could I use that to solve for the c value and then actually get the equation of this red parabola? Could I? Yes, right? But I don't need to. If I have the slope field and I know the point, I can actually just get the graph by plotting the point in the slope field and then just kind of flowing the rest of the graph through the slope field. Could I use this to plug in and solve for the c? And then could I get the equation of this blue parabola? Yes, we could. But again, you don't really need the equations. Could I get the equations of this? Could I get the equation of that? Yes, but you don't need them to get the graph. Now the graph itself, right, the slope field is really the visual representation of that general solution, right? The slope field is every single function that has this as the derivative, right? Which means it's going to be this kind of family of parabolas. Now the vertical shift, the c value, of course, that's going to be different based on whatever condition you want to satisfy. But the slope field represents all of them. All of the parabolas that would have this as the derivative. Regardless of the vertical shift, all of the parabolas would satisfy the slope field. Okay, so the slope field is like the graph of the general solution. All of the potential things that could fit, and then particular solutions through a specific point, those just kind of flow through the slope field. Okay, but here we go. Let's do the next one. Now notice this next one is only dependent on your y values. So here, instead of everything in the same column having the same slope, here everything in the same row is going to have the same slope. Because whether you're going to pick this point or whether you're going to pick that point, the x value of 3 versus the x value of -3, that doesn't matter because there's no x's in your formula. Okay, if you need to, you can make the little table. I'm not really going to. I'm just going to talk it out with you guys. Okay, so if I wanted, I guess we can do the table a little bit. The table kind of helps a little bit. X, y, y prime. I guess I should kind of get rid of that so you can see it. Now, again, the x value doesn't matter, so you really don't even need it in the table. Let's test something on the x-axis. So if your y value is 0, you plug in, you do 1/2 of 0, so that's 0. So everything on that x-axis is going to have a 0 slope. Now be careful, you probably want to like make those like a little bit of extra noticeable, because if you just do something like that, you can't really see the horizontal line. So you just like be obnoxious, put it like slightly above, make it extra thick and extra bold. Make sure you can see that like, hey, I didn't just leave those lines blank. There's actually horizontal slopes at all those points. Yeah, so oh, that looks terrible. I don't like it. I'm going to redo it. So here we go, like 0 slopes at all those points. So there's 0, 0, 0. Right? If you just do it once, like it's kind of hard to see, right? So just like make it a little bit extra thick. There we go. That looks probably about the same as what I just erased, but I'm going to pretend it looks better. All right, let's do the row right above it. If the y value is 1, 1/2 of 1 is 1/2. So everything in this row had a slope of 0. Everything in this one's going to have a slope of 1/2. And see, 1/2, so we go up 1 over 2. So I would be kind to connect those 2 points. So let's see, here we go. Let's try to make it not too bad. And then once you got one of them that's not too bad, you can just kind of do the rest parallel to it. And let's test the row up above. If the y value is 2, 1/2 of 2 would be 1. So everything in this row is going to have a slope of 1. I like 1s and 0s. That's just, you're perfectly diagonal, right? You're just kind of aiming down right for that next point. Should be slightly steeper than the slope of 1/2. And so here we go. Now let's see what these patterns are going to be. If I tried to test anything down here with the -1 coordinate, the slopes would end up being -1/2. So let's look at the pattern. We had 1, 1/2, 0, -1/2, and then this one will be -1. If there's any doubt, you can always just test the points to check. But I'm not gonna. Once you kind of pick up the pattern, you don't really have to keep testing points. You can just fill out the rest of the pattern. So let's go for it. Slopes of -1/2. So let's see if we can go about this point and that point, right? That's going to be a -1/2 slope. I don't know, it's not terrible. And if you got one of them, you can kind of just do everything parallel to it. And then we would need the slopes of -1. So let's just look at like those two. That's not too bad. That's a lot harder to do on the smartboard than I thought it was going to be. Oh well. So there's our slope field. That's the visual representation. Could I integrate this? Yeah, you could kick the y over, and then you could kick the dx over. Could I integrate? Sure. Ooh, I definitely forgot the dy, didn't I? So it'd be 1 over y dy, which then integrates ln of y, and then that would be 1/2 x plus c. And then if you exponentiated, you could get that the absolute value of y is going to be c e to the 1/2 x. So you would get this y. It could be plus or minus, depending on what type of y coordinates you wanted, c e to the 1/2 x. So it looks like these functions should be exponential. When we kind of glance at that slope field, do we believe it? Do we think that those graphs look like they could be exponential graphs? I don't know. Let's go do some general solutions. Let's go do some particular solutions. And let's go through the same points. Let's go through the point 1, -1, which is over here. Okay, so if I wanted to go through that point, could I use it to plug in right here and solve for the c value? Yeah, you'd be using the negative, right? You'd be using the negative to get the negative y value output. But you could use that condition to solve for c. But I'm not going to. I'm just going to kind of go and flow the graph through the slope field. Now here, that x-axis is actually going to be a horizontal asymptote. It's going to get closer to that slope of 0, but never really quite get there. So there we go. We've got that one done. And then let's go do the other one. And why not? Why don't we just go through the same point? How about the 0 and the 1, which would be right here. You could use this condition to plug it in, but here you'd be using the positive exponential since you have the positive y value. That kind of looks like a smiley face, kind of, almost. I don't know, maybe I'm just tired. But you could use that point to pretty easily then get the rest of this graph. You just kind of flow it through the slope field, and you would have that horizontal asymptote as you go to the left. Do you believe that both of those are exponential? So you have the one that's been reflected vertically downwards, and then here we have the blue one, which more looks like that typical exponential. May even just be e to the x, since it's going to go, I guess it's not e to the x, so we know it's going to be a 1/2 x. So it's got a little bit of a horizontal stretch to it, but do we believe that those graphs look exponential-ish? Yeah, right? We can, for these two examples, we could separate and integrate, and we could use the conditions to actually get those equations, but in order to graph them, you really didn't have to. The general solution, right, this whole graph is represented by the slope field, right? It's all of the potential graphs that have this as the derivative. Could I actually find what the equations of those particular solutions are? Sure. Do you need to? No, right? If you have the slope field and you know a point that the particular solution wants to go through, you just plot the point, make sure you go through the point that it tells you, and then you can just flow the graph through the rest of the slope field. Right, so they're tedious, they're a little bit annoying, finding the slope at each one of those points, and then drawing the little lines, and then if you have a particular solution, doing it through the slope field, yeah, it's nothing very hard. It's just a little tedious and time consuming. Let's move on to the next example. Alrighty, here we go. Now this one, oops, as I turn it all sideways, this one is going to have x's and y's. How exciting for us. So let's go ahead and let's go for it. This one, you may just want to make a table. Is it on the pin? Yep. So we go x, y, and then y prime. Let's go test some coordinate points, and then let's find out. I always look for the easy ones first. Like I'm thinking about that differential equation, which is x minus y. Let's go find the 0 slopes. right? So add the y over. Anywhere that the x value equals to y, anywhere on that line, y equals x, right? There's your line y equals x. Anywhere on that line, your slope is going to be 0. If the x coordinate and the y coordinate are the same, then x minus y will be 0. So the origin would be a slope of 0. The point 1, 1 would have a slope of 0. The point -2, -2. If the x and the y's are the same, right, all those points are going to end up giving you the slope of 0. So here we go. Let's go graph those. That's a slope of 0. That's a slope of 0. That's a slope of 0. That one and that one. So here, everything on that diagonal had a slope of 0. Right? This one looks like it may be a diagonal pattern. Let's test it, right? Don't blatantly, blindly fill out the rest of the slope field unless you're 100% for surezies you know what the pattern is. Let's go test something. Like how about the point right here to the right of the origin, which is the point 1, 0. Now this function, the slope field, says x minus y. So 1 minus 0, that gives us 1. So then the slope on that point would be 1. Let's go test another point on that same diagonal. Like how about this one or this one, right? It doesn't matter. Let's test another one of those. Let's do the second one I did, which is 2, 1. 2 minus 1 would be 1, right? So that point is going to have a slope of 1 also. This one will also, as will this, as will this. All the points on that diagonal will end up having a slope of 1. If you don't believe me, just check it. Okay, just check it. Just always plug in the coordinates into the slope field and compute them. But everything on that first diagonal had a slope of 0. Everything on that diagonal has a slope of 1. Let's just probably test this one. Like here, that's the coordinate point 2, 0. X minus y, 2 minus 0 is 2. So everything on that next diagonal is going to have a slope of 2. So let's go look at trying to connect those two. And then I'm glad the camera's off because I would probably look pretty stupid trying to do this really quick. It's hard to do it on the smartboard. I'm just going to wing it. Okay, slope of 2, and then slope of 2, and then slope of 2, and then slope of 2. Yeah, okay. Doesn't look super great. Yeah, okay, whatever. Then everything on that next diagonal is going to have a slope of 3. So that's going to be even steeper. And then those 2 points on the next diagonal are going to have a slope of 4. And then that poor sucker right there is going to have a slope of 5. It's going to be nearly vertical just based on the grid that we're given. But this one, it's based on x's and y's. Now, it happened to be a diagonal pattern. That won't always happen. But this one did end up giving us that very nice diagonal pattern. We had 5, 4, 3, 2, 1, 0. Now, I would test it. Sometimes you see the patterns that continue. -1, -2, -3, so on and so forth. Or sometimes you have the patterns that are kind of symmetrical on the other side. So it could be just 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. Like sometimes I could see that this next row could conceivably be 1s, and then you would just count up again, or it could be -1, and you could just keep counting down. So you'd want to test it. But if you plug in anything from that row or from that diagonal, like how about this point, which is the point 0, 1, x minus y will be -1. So everything in this diagonal will be a -1 slope. So -1, -1, -1. And then everything in that next diagonal is going to be -2. And then those 3 points on the next diagonal will have a slope of -3, which would be steeper than the -2. And then those would be your -4s, and then that one's your -5. Okay. You know, if this was the AP exam, would I probably want you to be a little bit more careful about how you draw the little lines on the slope field? Yeah, like if it was the real AP exam at the end of the year, I would probably take a little bit more time. But really, up until then, it's okay. Like it doesn't matter. It's okay. Let's go through. So that's the general solution. Let's go back and let's look at this. Remember, if there's any doubt at all in your mind about how to fill in the slope field, just always test the points. And if you're not sure about what the pattern is, just test the points and plug in all the coordinates of all the points. If you're unsure about what the pattern is, just test all the points. No worries. Now, is this differential equation something we could separate? No, because really we have the addition. You could try to add the y over and get like y plus dy but really you'd have something like this. And then if you tried to multiply by dx, well, then the dx would pick up that chunk too, and then there'd really be no way to separate that without then putting the dx. Yeah, it just wouldn't work, right? This differential equation right here would be non-separable. And so we will occasionally see stuff that's non-separable, but it will never ask us to integrate that non-separable stuff. We can still do the slope field for it, but we won't have to separate and integrate it because we can't. Okay, not right now. There's entire classes in college over differential equations where you will learn how to work with those non-separable things. There's like different degrees of difficulty. Okay, you'll if you ever take that class, you'll figure out that, hey, these separable ones that we saw in Mr. Bell's class, they really weren't very bad. I wish I could go back to the separable. But here it's non-separable. Okay, but we didn't need to integrate it. It's okay. Let's still do some particular solutions though. And let's go back and do the same points that we did earlier. How about let's go through the point. I think we did 1, -1 in red. So let's go through the particular solution through these specific points. 1, -1, here we go. That's what the point would be. It's got a slope of like, I think that was the slope of 1, 2 right there. So it's got a pretty steep slope. And then it's going to kind of do something kind of more or less like this. And then it's going to kind of actually go down pretty steep. You make sure you go through the point, and then you kind of just generally flow the slope field through the rest of the graph. And it may not end up looking super pretty. Like I just made that one worse with that last little line. But yeah, you just make sure you go through the point that it tells you, and then just generally flow the rest of the graph through the slope field. Let's do another one. I think I did the point 0, 1, which would be this guy right here. Now remember, somewhere on that axis, kind of somewhere on this imaginary line, actually we never did it, but oh yeah we did. Somewhere on that line y equals x, right? Somewhere on that diagonal right here is where your horizontal tangent will be. That's where your minimum will be if we have it. So let's do this graph. Here it's got the slope of 1. When it kind of crosses this imaginary y equals x line, right? This point where it crosses y equals x, that's the point where you'd have the horizontal tangent. And then here it's going to kind of do something, I think, more or less like this. It's going to be kind of like a lazy asymptote or a lazy parabola, where it leans a little bit over to the right, and then it goes up a little bit more steeply on the left. Is it a parabola? No. If it was a parabola, it would be an x squared type function. So if it was a parabola, the derivative would have just been linear. Right? Since that derivative has x's and y's, we know it's not probably just a basic parabola. It's got a little bit of a lean to it. That's okay. We don't really need to know what that parabola is. We can still get the graph of it through doing the slope field. And remember, anywhere you were kind of crossing this axis, y equals x, that's where you would have the minimum, or that's where you would have the horizontal tangent. Let's do one more for this guy, and then we'll move on. Let's go through the point. How about -1, -1? Which that point would be right here. So that point would be the minimum. And so that point's the one that has the horizontal tangent. And then that one is going to go kind of over towards this oblique asymptote, that slanted asymptote. And then over here, it's going to go up, up, and up, and up, and it's going to get steeper and steeper. So there you can see it's kind of like a parabola, but it goes up steeper on the left and kind of leans over towards that slanted asymptote on the right. Yeah, well, we have those 3 particular solutions through the slope field. There we have it. Now, slope fields themselves aren't super difficult, right? It's just algebra. Like, literally, it's all algebra. Plugging into that formula to get the slope, graphing the little lines at all those points with those slopes. It's not too bad. Okay, but is it annoying? Yes, it's certainly annoying. Let's flip it over. Let's do like 1 or 2 more examples in this video, and then we will break. All right, so let's clear that one out. Clear it, Steve. All right, let's go to the next one. I need the arrow, and then I need to hit the next. Cool. I believe at the top of the next page, we have a multiple choice question. And then we'll do this multiple choice, and then we'll do this free response, and then we'll call it for this video because I want to go home because this is Friday before spring break, and then I want to go home. All right, here we go. Sure, green's fine. says the slope field for a certain differential equation is shown above. Which of the following could be a specific solution to that differential equation? This one's not rocket science, guys. Let's just plot a point. Like what would a particular solution look like? Let's just go for it. Let's just go through the origin. If I was going through the origin, you can see it's going to do something kind of like that, and then it's going to do something, kind of like that. Well, what type of functions look like that? I'll give you a hint. They're not sinusoids. They're not cosines, which are also sinusoids. If that was my original function looking like it, that one wouldn't be quadratic and it wouldn't be a natural log. That one looks more like a cubic function. Okay, so if it gives you the differential equation, you can kind of just, or if it gives you the slope field, if it gives you the slope field, if you graph one particular solution through it, remember, that is what your original function would look like. So if your multiple choice answer options are y equals, if they're the original functions, you just pick which equation does that graph look like, and that one definitely is cubic. But here's kind of a curveball that they will sometimes do for you. What if instead they had done this? What if they said y prime was sine of x? Or what if for b, what if they said y prime was cosine of x? And then for c, what if they said y prime was x squared? And then y prime is 1/6 x cubed. And then for e, what if they said y prime was L of x? What if instead of all of the options being y equals, what if it gives us y prime equals? Now here it's tempting, right? The graph that we can see is cubic, obviously. But remember, the graph that you can see is y. And if your original is cubic, we don't necessarily know. It could have some coefficients. It could have some extra vertical shifts or whatever, but we know in general it's cubic. If the thing that I can see, which is y, is cubic, what would the y prime be? It would be quadratic, right? It would be 1 degree less. So if your answer choices were y prime equals sine, okay, sorry, that one's still terrible. Or y prime equals cosine. No, that's terrible. Thanks for playing. The natural log graph. Okay, if you picked any of those three, you're just like the world's worst guesser. Okay, like get better at guessing. But if your options were what does y prime equals, the answer would not be the x cubed answer choice. It would be the x squared answer choice. The thing that you can visually see, right? If you graph a thing through the slope field, that's a y equals. That's a particular solution. So if you have, like this question started as, if you have y equals, it's really easy. What does that graph in your slope field look like? It's cubic, therefore pick the cubic. But if you're trying to match the slope field to the differential equation, to the derivative, then what that graph looks like is not going to be the equation of your answer, because you're looking at the original, and then the differential equation is what does the equation of the derivative look like? So it gets a little bit harder. Always pay attention. Hey, that thing that I can see in the graph, that's y. Am I matching it to the y, to the original function, or am I matching it to the y prime, to the dy dx? If you're matching it to the differential equation, right, and those could have easily have been dy dx instead of y primes. If you were matching it to the differential equation, the answer choice may not be exactly what it looks like. Because remember, it gives you what it looks like is the original function. And then your differential equation would be the derivative of that thing that it looks like. So those get a little bit tricky, just be careful. Don't get got by them. But yeah, those slope field ones, visually, what you can see through it is the original function. So if you're matching to the derivative, just be careful. Let's do one more, and then I'm done. Here we go. Sure, red's fine. Actually, I don't want to use red. Let's use purple. I like purple. Consider the differential equation dy dx equals xy over 2 on the axes provided. Sketch a slope field for the given differential equation. Now, that's a pretty small grid. Typically on the AP exam, the grids that they give you are going to take up like half a page or so, right? And so that same grid, I just shrunk it down just so the sake of saving space in my notes packets, that grid looks visually small. Now, it's a 6x4 grid, so it's 24 dots. It's not huge. Generally, the bigger the grid is, the more dots you have. Generally, the easier the pattern's going to be. The smaller, the fewer the grid points you have, typically the harder the pattern is going to be, right? If they give you a really big grid, the pattern's probably pretty easy so that you can fill it in fairly quick. If it's a smaller one with only like 8 or 12 or so points, you may just have to test them all. But visually, I just shrunk that down so that it would fit in my notes. But they always give you graphs that are like plenty big. But here, let's do the slope field. And then on part B, we're going to find the particular solution that satisfies. Actually, we're just going to graph the particular solution. Then on part C, we're going to find the equation. We're going to make an estimation, and then we're going to look at the error involved. Okay, so here we go. Let's do the slope field first. Actually, yeah, I'll do the slope field in purple. Here we go. So slope field. So let's go test some points. If you need to, just always organize it. Oops, with the table. I always look for the easy things first. Like if I've got this, and if I want the derivative to be 0, that would happen when either the x is 0 or the y is 0. Right? If x or y is 0, that whole slope is going to be 0. So I always look for the easy ones first. So there we go. All those points are the ones that are going to give you 0 slopes. Easy, right? Now let's just go plug in the rest of them. Like how about the point 1, 1? 1 times 1 divided by 2 would be 1/2. So at that point, I need a slope of 1/2. And then let's do the point to the right. Let's just finish that row kind of right above the 0 row. If I did the point 2, 1, you do x times y divided by 2. So 2 times 1 divided by 2, that would be 1. So here we go. That one's a slope of 1. Then the next point would be 3, 1. 3 times 1 divided by 2 would be 3/2. So I'm thinking I see a pattern, right? That was 0. That was 1/2. That was 1. That was 1.5. That's your 3/2. So the slopes get steeper each time, but it gets like a steeper by a 1/2, right? So that little row is counting by 1/2. So you had 0, 1/2, 1, 1.5. Let's go check. Let's go check this one where it's -1, 1, x times y divided by 2. Okay, so there we go. That's -1/2. So my pattern is going to continue. It's 3/2, 1, 1/2, 0, and this one's going to be -1/2, and that one will be -1. Right? So everything was counting by 1/2. Moving from left to right, you were counting by 1/2. Let's go look at the row right above it. Let's test this point, which is the point 1, 2. X times y divided by 2. So 1 times 2 is 2, divided by 2 is 1. So here we go. That's a slope of 1. If I test that point, that's 2, 2. 2 times 2 is 4, divided by 2 is 2. So the slope at that point is 2. Let's look at this pattern, right? That's a slope of 2. That was a slope of 0. That's a slope of 1. That's a slope of 2. Let's see. What do we think that one's going to be? It's the point 3, 2. 3 times 2 is 6. 6 divided by 2, oh, that's right, it's 3. So this one is counting, that one's counting by ones. So that was 0, 1, 2. That one's 3. This one's going to end up being -1. And then that one's going to end up being -2. Okay, so we're counting by ones to go across that top row, counting by 1/2. The x-axis was just zeros. And then if we were to test any of these points, like how about, all right, we can always just make the table bigger if we need to. Get out of there. X times y divided by 2. Let's actually just get that. Can I get that off the screen? Do you not want to go down? Nope, he doesn't want to go down there. Okay, thanks, Steve. If I were to test this point, which is 1, -1, x times y divided by 2, so that would be a -1/2. So this one's -1/2. This one's going to be -1. That's your -3/2. This one's also counting by 1/2, but it's really like a -1/2, right? So that was 0, -1/2, -1, -3/2. This one would actually be the +1/2, and that one would be your +1. And so there we have it. A little bit of work. It wasn't a terribly hard slope field. There was kind of a little bit of a pattern. It was just a little bit weird. But yeah, there we have it. And then I didn't really need to test. Remember, you don't really need to test all the points. You need to test enough of the points so that you can see the pattern. But once you get the pattern, no, I didn't want to do that. Stop it. Once you get the pattern, you don't really need to test any more points. Okay, but there we go. Part A is done. We got the slope field done. Hooray. Let's look at the part B. It says, let f be the function that satisfies the given differential equation. Write an equation for the tangent line. Here we go. Equation for the tangent line. Y minus y1 equals mx x minus x1. Those should always just, that point slope should always just jump right to the top of your brain when you see those 5 words. Through the point 1, 1. So it gives me the x1 value and the y1 value. And then we're going to use the tangent line to make an approximation. Okay, here we go. Let's go back. Here we go. That was actually the first point I tested, right? There's your m value at the point 1, 1. The slope of that point ended up being 1/2. So my tangent line is going to be 1/2 x minus 1 plus 1. You could distribute the 1/2 if you want. I would just leave it. I would just leave it. If you wanted to distribute it, that's fine. But we got the equation for the tangent line. So we've done that part. And then it says use the tangent line to get an estimation. So let's go for it. We're going to take that function. We're going to plug in 1.2. So we've got 1/2, 1.2 minus 1. So that's 1/2 of 0.2. 1/2 of 0.2 would be 0.1. So I've got that the tangent line is equal, that's 1/2 of 0.2 is 0.1, so I've got 1.1. Right, so the tangent line is 1.1. That means my function, you know, the thing that we can't see, but the function is going to end up being about 1.1. We use a tangent line to get an approximation. The tangent line is, right, the tangent line is equal to 1.1. That means my function is going to be about 1.1. And then that's everything it wanted us to do, right? We got the equation for the tangent line. Then we said use the tangent line to get an estimation. Very good. So we're done with everything on part B. Let's now move it over and let's do part C. Now it says find that solution. And then once we have separated and once we have integrated, then we can actually find the true exact value of f of 1.2. Okay, let's take this guy. I'm going to come do that work over here. And then let's separate and integrate. The y is going to have to divide over. So I've got 1 over y dy. That 2, I'm just going to rewrite it as a 1/2 coefficient. So there we go. There's the algebra, right? To separate the x's and the y's. You need the y to come over to the left, and then everything else on the right. If I were to integrate, we'd have ln of y equals 1/4 x squared plus c. We're going to exponentiate. So I'm going to get that y could be plus or minus c e to the 1/4 x squared. Or you could leave the absolute value if you want. I just dropped the absolute value and I put a plus or minus. That's great. There is your general solution. Now let's go through and let's use this condition. I guess I can finish. Yeah, I guess I'll just kind of take this work. I'm trying to like not erase everything, but I may have to. Then let's go for it. So I know it's going to be a positive y values, so I can just kind of like drop this, right? I'm not going to need the plus or the minus. I'm only going to need the plus. For 1, the y value is going to be equal to c e 1/4 of 1 squared. So 1 is going to be equal to c e to the 1/4. Therefore, divide that exponential over. I'm going to get that c is equal to 1 over e to the x to the 1/4, or e to the 1/4, otherwise known as my c value is e to the negative 1/4. That's an ugly c value, okay, but that's all right. We can live. We can make do with it. And then let's take that c value, plug it in, and then we'll get this general solution. So I've got y, or we could leave it as y, or we could change it to f if you want. Let's change it to f. Might as well. So f of x. Come on. So frustrating sometimes. F of x. Let's go back up here. We got the c value. Let's plug it in. So I had e to the negative 1/4. And then we had e to the 1/4 x squared. You could actually combine those things. I'm kind of running out of room. So let's combine those. And here we get that this function f of x, we're going to have an e. And then I have a negative 1/4 and a 1/4. I'm going to factor out the 1/4. And then I have the positive x squared minus 1. So there's what your function could end up looking like. You had to separate, integrate, use the condition to solve for c. Once I plugged it in, then I could kind of recombine the exponentials. But there we go. Right now we've actually found that function. And then once you have the function, we could find f of 1.2. So f of 1.2, if you were to actually plug that in, we would just use the calculator, plug that in, and then you would end up getting 1.116. And then that would be the exact solution that your function goes to. Okay, so C is where it wanted us to separate and integrate, but it was separable, so that's really nice. Let's check. How did my estimation compare to the true value? Here was my estimation. Here was the true value. Did our tangent line give us a pretty good approximation? Yes, right, it was pretty nice. Tangent line was a pretty good guesstimation for us. But was it an exact answer? No. So last part, compare my estimate, which was the 1.1, to the actual value, which is the 1.116. And then let's figure out, was it an overestimate or an underestimate? And then let's look at the error that was involved. I'm gonna just get rid of all of this stuff. I'm gonna hope and see if that's gonna work. Yeah, there we go. All right, so let's just, sorry, I had to erase it so I had some room. So let's look at the error. The error is just the absolute value of the exact minus the approximation. Let's figure out how far off we were. We had 1.116 minus 1.1. So here my error is going to end up being 0.016. Right? So that's not a huge error. That's not too bad, right? There's my error. And then did we have an under or an over? Well, the exact, I guess we should say, which one was bigger? Here was the exact value. Here was the approximation. It looks like the approximation was too small, right? Y of 1.2, that was my 1.1, was less than F of 1.2 because that was your 1.116. Therefore, we had an under estimation, or we had an under approximation. And then your explanation would be something like this, because I can literally look at the two numbers and I can judge which one's bigger. Therefore, I can conclude which one was the under, or if it was an under or if it was an over. Also, if you were to look at this subtraction, right, kind of the order and the corresponding result will also tell you whether you have under or over. If I took the exact minus the approximation, and if I got a positive result, this is before the absolute value. The absolute value, when we're looking for the error, is just going to say, hey, what's the size of the gap? How far are those two apart from each other, regardless of which one's bigger? But if I did exact minus approximation, and I got a positive, well, that would mean the exact is bigger than the approximation. If you do subtraction and it's positive, that means this one's the bigger term. Right? So then the exact would be bigger, which would give us an under approximation. Or if I did exact minus approximation, and if I got a negative value, that means the approximation must have been bigger. Right? The bigger chunk was getting subtracted. Or vice versa. If you, if you were to have switched it, and if I were to do approximation minus exact, and let's say if that was positive, well, if you did approximation minus the exact, whenever you do subtraction, and if you get a positive result, that means the approximation, the first term, would have been bigger. Or if you did the approximation minus the exact and you got a negative result, if you do subtraction and you get a negative result, that means the thing that was being subtracted was bigger. So really, the order of the subtraction and the sign of the result of that difference, that will also tell you if you have an under or an over approximation. You have to just think, though, what was the order in which I subtracted? What was the value of my difference? So therefore, which one of those two things is larger? But also, if you can just physically and visually compare the two results, you can just say, I had an underestimate because my estimate was under and less than the exact value. It doesn't have to be harder than that. You can think about it in some other ways, but it doesn't have to be harder than that. All right, I'm going to wrap it up right now because, oh my gosh, it's already like 4:15. I'm done. We will come back in the next video, and then we will finish the last of these couple of examples with slope fields. But I am done for today. Thank you guys for watching.